What if I told you the most important leap in rail technology didn't come from Japan, Germany, or the United States, but from a small African nation few people had ever associated with modern trains? 2 months ago, an unexpected post appeared on a U.S. rail enthusiast forum claiming that a new propulsion system developed in Saine had achieved what American engineers had struggled with for decades. At first, the community dismissed it as another overhyped rumor. But then, a 45-second clip surfaced showing a freight train accelerating almost silently, with no visible emissions, no overhead wires, and no diesel engine exhaust. That single clip changed everything. Within hours, major U.S. Railfan pages on Reddit and Facebook were flooded with debates, technical breakdowns, and disbelief. Seasoned rail enthusiasts began dissecting the footage frame by frame, searching for clues. Was it magnetic levitation, linear induction, or some hybrid system that defied existing classification? The first analysis came from a retired Amtrak engineer who admitted, if this footage is real, we're looking at something fundamentally different from anything in our current design playbook. For a community obsessed with locomotives, couplers, track gauges, and heritage preservation, it was an earth-shaking moment. But who or what was Saine? Most Americans had never even heard of it. Saine, a small but ambitious African nation, had recently poured unprecedented investment into research on sustainable transportation. Its rail sector, while modest compared to the giants of the world, had quietly become a laboratory for unconventional engineering ideas. Behind this wave of innovation stood a collaboration between Saine's National Rail Research Institute and a startup of young engineers formerly working in renewable energy systems. Their mission was deceptively simple: make rail transport cheaper, faster, and self-sufficient in energy. The result was a propulsion system that shocked not just the rail community, but the entire transportation industry. The system didn't rely on traditional combustion engines or even external electrical supply. Instead, Saine's trains utilized what engineers described as localized magnetic flux induction, a new method of generating continuous motion from contained electromagnetic loops without requiring a constant power feed from overhead lines or third rails. In simpler terms, the train created its own propulsion energy through a closed electromagnetic process, recycling it dynamically along the rail line. It was the rail equivalent of a self-sustaining electric ecosystem. To many U.S. rail fans, that explanation sounded like pseudoscience, until technical papers began appearing online detailing the experiments, the hardware, and the early results. One of the documents published by Saine's National Rail Research Institute described how the rail lines themselves were embedded with conductive alloys capable of resonant energy transfer. As the train moved, the energy generated from its own momentum interacted with the alloy beneath, creating a regenerative propulsion effect. The concept wasn't entirely alien. It borrowed from known magnetic induction principles used in wireless charging. But Saine's team had scaled it up to rail infrastructure in a way no other country had ever successfully achieved. The U.S. railfan community was stunned. Every discussion thread began with disbelief and ended with admiration. One popular comment summed it up perfectly: "We've been dreaming about this kind of system for 40 years, and now an African country just casually demonstrates it on a test track." In the days that followed, YouTube channels dedicated to rail technology posted video breakdowns analyzing the system's potential. Many pointed out that Saine's trains could eliminate the need for costly diesel imports and reduce carbon emissions to nearly zero. Others marveled at the implications for maintenance. Since the engines were modular and self-regenerative, they could theoretically run for decades with minimal servicing. This was the kind of leap that could redefine not just Saine's transport infrastructure, but the global economic structure around freight logistics. If proven scalable, Saine's design could challenge traditional energy models in rail systems worldwide. For the U.S., it hit especially hard. America's rail network is vast, but much of it is outdated and heavily dependent on diesel. attempts to electrify major corridors have faced enormous costs and political challenges. The idea that a small African nation had found a cleaner, cheaper alternative was humbling and, to many, inspiring. Railfans in the U.S. began drawing comparisons to the golden era of American rail innovation when the country once led the world in locomotive design. Saine's discovery rekindled a sense of possibility long thought lost. Engineers from multiple American universities reached out to Saine's researchers for collaboration. Even a few private freight companies reportedly expressed interest in licensing the underlying magnetic flux technology for pilot programs in the Midwest. By now, mainstream media had caught on. Major outlets began running headlines like Africa's Rail Revolution and Saine's tech could outpace Japan's maglev. The story snowballed into a global phenomenon. But beneath the hype was a genuine question. How does this new system actually work in real-world conditions? Saine's engineers were cautious. They emphasized that their prototype was still under controlled testing. However, the data they shared was staggering.
The first operational line, only 8 kilometers long, demonstrated sustained speeds of 280 kilometers per hour with energy regeneration efficiency exceeding 90%. That meant the train was recycling nearly all of its motion energy back into the system, drastically reducing external power needs.
The most astonishing part wasn't the speed, it was the silence. Observers described the train's motion as eerily quiet, almost gliding, with no mechanical rumble or track vibration typically associated with high-speed travel. Saine's team claimed that the conductive alloy tracks not only aided in propulsion but also absorbed and dampened vibrations, increasing comfort and reducing wear. When footage of passengers experiencing the prototype ride went viral, it further fueled fascination among U.S. enthusiasts. To the average viewer, it looked like a scene from a science fiction movie. But to rail engineers, it represented decades of theoretical ambition finally realized. American engineers couldn't help but reflect on the limitations holding them back. The United States has struggled with bureaucracy, infrastructure aging, and funding constraints in modernizing its rail systems. In contrast, Saine's relative lack of legacy infrastructure gave it the freedom to innovate from the ground up. Instead of retrofitting outdated tracks, Saine designed new ones optimized for electromagnetic coupling. This clean slate approach was something U.S. engineers could only dream about. What further astonished analysts was the cost efficiency of Saine's design.
Because the system reused locally available minerals and alloys, the overall infrastructure cost was significantly lower than traditional electrified rail. Some reports estimated that Saine's per kilometer construction cost was nearly 40% cheaper than comparable maglev systems in Japan or China. Economists began to take notice.
They suggested that if Saine's model proved economically viable, it could open a new industrial chapter for Africa, one where the continent exports not raw materials, but high-end transport technology. U.S. rail fans couldn't help but see the irony. For decades, Africa was viewed primarily as an importer of technology. Now, Saine was positioned to become a global supplier of next-generation rail systems. Online discussions among enthusiasts often drifted into philosophical territory. How did the world overlook the potential of regions like Saine, where necessity drove creativity beyond conventional boundaries? It was a humbling reminder that innovation doesn't require massive budgets, only vision and courage to question norms. The proof of concept had now attracted attention from the European Union and several Asian partners. A few transport ministers even hinted at international trials to validate Saine's results under diverse conditions. Meanwhile, in the U.S., transportation policy experts began debating how this might influence future infrastructure plans. Could America realistically adopt Saine's model without overhauling its entire rail foundation? Some argued yes, pointing out that freight lines in the Midwest could serve as testing grounds. Others were skeptical, citing regulatory hurdles, intellectual property complexities, and entrenched industrial interests. Still, the sheer potential of Saine's discovery ignited imagination across borders. One American commentator described it as the Tesla moment for rail. The comparison wasn't far-fetched. Just as Tesla redefined electric mobility, Saine was redefining rail propulsion through unconventional physics. The difference was that Saine's system didn't depend on massive lithium-ion batteries or external grids. It generated, used, and regenerated power in one continuous loop. That simplicity made it profoundly scalable. U.S. rail enthusiasts began speculating about hybrid applications. What if this technology could power light rail networks in cities or autonomous cargo systems in ports? Suddenly, the possibilities seemed endless. Rail museums, engineering schools, and YouTube creators began producing explanatory videos to help the public understand what Saine had achieved. Some went viral, with titles like The African Train That Powers Itself and Saine's Discovery That Defied Physics. The phrase Saine effect even became a trending topic among engineers online, but beyond the excitement, deeper discussions began around the environmental implications. If Saine's system truly eliminated external energy dependency, it could drastically cut emissions from one of the most energy-intensive industries on Earth. That realization turned heads in climate policy circles. For years, international efforts to decarbonize transportation had focused on electric cars and aviation fuels. Rail had been somewhat neglected, seen as efficient enough. Now, Saine had shown that even efficiency could be revolutionized. The International Energy Council reportedly reached out to Saine's government to explore collaboration. Saine, aware of its newfound spotlight, established a dedicated innovation council to manage technology transfers responsibly. The goal wasn't to monopolize the discovery, but to ensure that its benefits were globally shared under fair terms. This move further impressed observers, contrasting sharply with the often secretive practices of industrial nations. For U.S. railfans, it wasn't just the technology, it was the attitude. Saine's approach represented a purer form of innovation, one driven by collective progress rather than competition. It reignited a conversation about what innovation truly means in the modern era. Meanwhile, early commercial partners began lining up. A South African logistics firm announced plans to integrate Saine's propulsion system into its regional cargo network by 2027. A Middle Eastern consortium reportedly proposed financing a 300-kilometer demonstration line. And in the United States, a small research group in California quietly began modeling Saine's electromagnetic resonance system for potential integration into urban light rail. Suddenly, Africa was leading a global conversation about the future of transportation. In online debates, many U.S. railfans admitted that Saine's success had reshaped their perception of African innovation. They weren't just surprised, they were inspired. One viral comment captured the sentiment perfectly. Maybe it's time the U.S. learns from Africa instead of assuming innovation only flows one way. That comment was shared thousands of times, even appearing in op-eds across major transportation blogs. But not everyone was convinced. Skeptics argued that the long-term sustainability of the technology was unproven. Could it handle heavy freight loads? Would it perform in extreme weather conditions? Saine's engineers responded with data from their ongoing trials showing adaptability across various terrains and temperatures. They explained that their design didn't rely on delicate superconductors like traditional maglevs, but on durable materials optimized for tropical and semi-arid climates. That practicality made it even more appealing. In a rare interview, Saine's chief engineer summarized their philosophy: "Our goal wasn't to chase speed, it was to chase sustainability." That statement resonated deeply with environmental groups worldwide. Soon, Saine's story became part of a broader discussion about Africa's emerging role in the clean tech revolution. For American audiences, it marked a cultural shift as well. Media outlets began covering African science not as novelty, but as leadership. In train clubs and rail museums across the U.S., enthusiasts started hosting events dedicated to discussing Saine's breakthrough. Model train makers even began designing miniature replicas of Seine's prototype engines. What began as a viral video had evolved into a global case study in disruptive innovation. The US railfan community, long nostalgic for the past, now found itself dreaming of a future shaped by Seine's ingenuity.
Transportation analysts began publishing white papers on how such technology could reshape logistics costs, regional economies, and energy consumption patterns. Some predicted that if Seine's system achieved international adoption, it could cut global rail energy demand by over 60%.
That kind of transformation could ripple across industries, from mining to shipping to urban mobility. It wasn't just about trains anymore. It was about reimagining movement itself. For decades, rail had symbolized the mechanical age of industry. Now, Saine was transforming it into an emblem of clean, self-sustaining technology. This wasn't an incremental upgrade, it was an ideological shift. The realization that energy could be generated, transferred, and recycled continuously within a transportation system challenged long-held assumptions about efficiency. The implications went far beyond rail. If Seine's principles were applied to other modes like cargo ships or hyperloop systems, the world could enter a new era of self-powered transport infrastructure. That's why, even months later, US rail enthusiasts remain fixated on Seine's discovery. They continue to follow every update, every test, every interview. Some have even begun lobbying for academic partnerships between American universities and Seine's institutes. For them, it's not just admiration, it's hope. Hope that the stagnation in US rail development might finally break. Hope that innovation could once again come from unexpected places. And perhaps most importantly, hope that collaboration, not competition, might define the next century of transport evolution. The goal is to demonstrate continuous long-distance operation without external energy inputs. If successful, it could redefine logistics economics globally. Experts are already calling it one of the most significant engineering developments of the 21st century. And it all began with a few curious rail enthusiasts watching a mysterious video online. That curiosity has since blossomed into global fascination and serious academic inquiry. From skepticism to respect, the journey has been nothing short of remarkable. Seine's engineers have remained humble, emphasizing that their discovery was the product of necessity and persistence, not magic. They often cite the lack of pre-existing infrastructure as their advantage. It forced them to innovate differently. Meanwhile, US railfans continue to discuss what implementation could look like at home. Could Seine's model be adapted to America's vast freight networks? Could it finally end the diesel dependency that costs billions annually? The answers remain to be seen. But one thing is certain, Saine has proven that innovation knows no borders. Its discovery has shaken assumptions, inspired debate, and reignited dreams once thought impossible. And as new data emerges, the fascination only grows stronger. Because what Saine discovered isn't just about trains, it's about the future of human mobility itself. A future where energy, motion, and sustainability become one continuous system. A future where inspiration can come from anywhere, even from a small African nation rewriting the story of global transportation. And that, perhaps, is the most shocking discovery of all.